An index fund generates an overall return of 300% over 10 years. What is the average annualized compounded rate of return for the fund? This is a problem which I hope will be very, very useful for understanding how important of a role mathematics play in certain real world applications. And this particular application is something that's very, very important to people all over the world, which is really, managing your money, savings, finances, investments, and so on. And this particular concept of compounded return is so very important that Einstein actually called it the eighth wonder of the world. Yet it's very, very underappreciated, I think, and it's not even taught in all schools around the world. I mean, I can tell from my example that it wasn't taught that well in my high school. So I hope that this will be an interesting lesson and something that my audience will take with them and actually be able to apply to the real world management of their money, savings, investments, and so on. So we'll start with a very quick refresher of a simple concept. And I've done this in my earlier video, but let's again revisit that. And that's the concept of percent and percentage change. So when we say X percent, it really means X by 100. So you can express that as a fraction, X by 100. And remember, X by 100 doesn't necessarily mean that X has to be less than 100. It could be any number. It could be more than 100. It could be less than 100. And when a quantity changes by X percent, and the change could be an increase, so that's indicated by plus, or it could be a decrease, which is indicated by a negative sign or minus sign. So when a quantity Y changes by plus minus X percent, what's the new value of the quantity? Well, the new value of the quantity is simply the old value. In this case, I'm assuming the old value was Y. So Y multiplied by 1 plus minus X by 100. It's a very simple formula to remember. So now let's start with the problem. We start by assuming that the principal initially invested was, the initial value of the principal was P. And some people like to start here with a round figure like 100 or whatever, and some say that makes for easier calculations. And it may be true in some cases, but I just want it to be as generic as possible. So just start with this algebraic notation, which is very generic. Let's let the starting principal be P. So what's the value of P at the end of 10 years? Well, P actually grew by 300%. So that's what it means, that the overall return of 300% over 10 years means that at the end of 10 years, P increased by 300%. So if that's the case, what's the value that the investment grew to at the end of 10 years? So the total value would be basically, and I'm representing the value of the investment at the end of 10 years by I10. So I for investment value and 10 is like 10 years within parenthesis. So this is equal to P multiplied by 1 plus 300 by 100, because P increased by 300. So hopefully you can relate it to the formula that I wrote in the yellow highlight. Y is equal to Y multiplied by 1 plus minus X by 100. So here X is basically plus 300%. So that's why I have 300 there. And Y is P, which is the starting amount, right? So I have basically investment at the end of 10 years equal to P multiplied by 1 plus 300 by 100, and that comes to 4P. So the money grew 4 times at the end of 10 years, which is substantial. So now we have been asked to find out what's the average annualized compounded rate. So, and that's not going to be, let me clarify that that's not going to be 300 divided by 10. That will be a mistake because, the math of compounded interest doesn't work uniformly. So if it had worked uniformly each year, then yes, then you could have probably divided by 10 and got some value there. But this is not an uniform, change every year. So let's start by assuming that the annualized average return rate be R%. And what that essentially means is, the money over any one year period increases by R%, but relative to what? So relative to the money or to the amount that it was at the start of the year. So it's basically, giving us the amount of change from the start of 1 year to the end of 1 year. And during this 1 year, that money grew from whatever it was at the start of that particular year by R%. So what's the value of the investment after 1 year? Well, at the start of 1 year, the value of the investment was P. And since it increased by R%, so the value of the investment at the end of 1 year is basically P multiplied by 1 plus R by 100. Simple. And here, because we are calculating the annualized rate, so we are not considering any kind of quarterly or monthly or in between the year compound effect, right? So it's basically an average annualized rate. So we're considering a average rate for the whole year, and that's R%. And we're assuming that the compounding effect is once a year. So that's the assumption here. So if that's the case, and we have basically the value of the investment at the end of 1 year is now P multiplied by 1 plus R by 100. So what's the value of the investment after 2 years? So let that be I2. So that will be whatever amount the money was before the beginning of the second year and at the end of the first year, which was, we just calculated that as the first step, right? The previous step. P multiplied by 1 plus R by 100. So that was the value of the investment at the beginning of the second year, right? And this grew further by R%. So the value of the investment after 2 years or at the end of 2 years will be whatever the value of the investment was at the beginning of the second year, and that grew by R% during the second year. So this will be basically P multiplied by 1 plus R by 100, and this whole thing will now get multiplied by again 1 plus R by 100, because this whole thing is now growing by R%, right? So if you want to relate this to the formula that I have in the yellow highlight, so your Y was now P multiplied by 1 plus R by 100, right? And X is simply R, and so positive, it's increase, right? So that's how we get. And if you do the math here, this comes to P multiplied by 1 plus R by 100 whole square. So that's the value of the investment after 2 years. So what would be the value of investment after 3 years? Well, at the end of 3 years, the value of the investment will grow by R% from whatever it was at the beginning of the third year. And what it was at the beginning of the third year, it's basically the same as the value of the investment at the end of 2 years, which we just calculated at the previous step as P multiplied by 1 plus R by 100 whole square. So that's what we started with at the beginning of the third year, and then during the third year, it grew further by R%. So we can write the updated value at the end of 3 years as I3 is equal to P multiplied by 1 plus R by 100 whole square multiplied by 1 plus R by 100. So that's the beauty of the compounding effect, because it keeps on, compounding on the value as it gets added. So it's basically compounding upon compounding, right? So this gets to 1 plus R by 100 whole cube, P multiplied by 1 plus R by 100 whole cube. And in this way, we can basically come to a conclusion, to a generic representation of what the value of the investment will be after n years. It's simply IN is equal to P plus R by 100 whole to the power n. And remember, here we are, assuming that the money gets compounded only once a year. So that's why it's an annual or average annualized rate, right? But if it was compounded, no more than once a year, then you have to take that into account as well. But this is a generic formula for compounded returns, right? And this is what Einstein referred to as the eighth wonder of the world. And why is that? Because the power of compounding is really, really enormous. And that's something, like I said, it's very, very underappreciated, because it's such a simple thing to some, but it could have really, really enormous effect. In fact, there is a quotation of Einstein saying that he who understands it earns it, who doesn't pays it. So that's kind of important to remember, that this is an extremely powerful effect, especially when it comes to savings and investing and finances. So now let's get back to the problem. So what would be the value of the investment after 10 years? Well, if we substitute n as 10, we get this. I10 is equal to P multiplied by 1 plus R by 100 whole to the power 10. So we know that this is equal to 4 times P, right? So we can equate these, and now it's a matter of solving an equation. And if we cancel out P from both sides, we're left with 1 plus R by 100 whole to the power 10 is equal to 4. So if we do or treat this like an exponents equation, we basically get this. 1 plus R by 100 is equal to 4 to the power 1 by 10. And from that, it's easy to get R is equal to 4 to the power 1 by 10 minus 1 multiplied by 100. So this is the average annualized compounded return. And this itself doesn't mean a lot unless I calculate this. So I used a calculator to find what the value of this one is, and it comes out to be 14.87%. So roughly like 15%. So that gives you an idea of the effect of compounding. By a compounding rate of 15%, your money can quadruple in over 10 years. So if you start with $1,000 and you get this kind of compounding effect, over 10 years the $1,000 will grow to $4,000, which is really amazing when you think about it, that a 15% effect, compounding effect, can quadruple your money or your investment. So that's why this is such an important concept. It's a simple one, but like I said, it's very, very underappreciated. But Einstein the Great, he basically called this the eighth wonder of the world. So there must be something to it, and I think it will be extremely helpful and useful in your practical life to be able to understand and appreciate the power of compounding.